Okay, so in this lecture, we are gonna introduce the concept of a complex field. Of a complex field. Now, this lecture will be a bit advanced in the sense of introducing the complex number as an abstract mathematical object. Students who are in currently their bachelors might find a bit difficult to relate to this very lecture, or students who need a quick introduction to what complex numbers are not quite advised to follow this lecture, because in this lecture, though we will be exploring the properties of a complex number, which is quite a bit important for students in 11 12 as well, because they also have a topic of on complex numbers, but that very much dedication of exploring the properties of a complex number will be much lesser than having a discussion on how we have constructed this complex field and what are the topological properties of this complex field. So without any further delay, let's just dive into this topic. So how have we thought of this complex field? First of all, now we know that most of the necessity of a mathematical number system, you might say, is completed by the real number system, right? Most of the polynomial equations have a root, have a real root. Moreover, the most necessary properties in mathematics of any uh, of any use, you might say, is kind of satisfied by the real number system. We have previously studied that the real number is a complex the real number is a complete field, right? Complete ordered field. So it has ordered properties, it's a field, and it's indeed complete. So there actually, on the first instance, there actually we don't get a need to construct a larger field which has some extra properties. But when we dive into the concepts of real numbers, or rather I should say the real field, we'll find that there are certain properties missing in the real field, and you might say the most important one of them is the absence of a root of this very equation, which is x square plus 1 is equals to 0. Okay. One of the definition of a real number is that x is a real number, x is a real number if its square is greater than equal to 0 and it is equal to 0 if and only if x itself is 0. Okay, clear? Got it? Okay. So this is obviously that this equation must have no real root, no real root, because if this has a real root, then obviously that number has a square -1, which is not possible for a real number, right? So the complex field C has been essentially constructed as an algebraic completion of R. So C is constructed as an algebraic completion of R, as an algebraic completion of R, that is, C is an algebraic, it is an algebraic extension of R and is algebraically closed. is algebraically closed. So I don't think viewers who do not have knowledge in field theory will understand these very terms. So I will just quickly explain them in very simple terms. That is, algebraic completion in the sense is that every polynomial in R will have a root in C. That is the very basic thing we want to say. So it is obvious that in such a case x square plus 1 will obviously have a root not in R but in C. Clear? And that is the other way of saying that C is algebraic extension of R. C's algebraic extension of R is what is basically is that every element of C is an algebraic element of R. Algebraic element in the sense that it is root of some polynomial in R. Clear? And algebraically closed is basically the meaning that every number in C is algebraic over C, or rather should I say that the set of all algebraic elements in C is just C. Clear? So basically this very line just says that every polynomial in R has a root in C. That is what we basically mean to say. Okay. Now we have some basic properties of C, right, which we have learnt in our junior classes, that every element in C can be written in the form of a plus ib, where a and b are real numbers, right? That if we consider z to be an element of C, then z is in the form of a plus ib, where a and b are real numbers, right? I is the square root of -1, right? And we had then the polar form of z, which was of the form r times cos theta plus I sin theta, where theta was said to be the argument of z, which was written mathematically as tan inverse of a b upon a, tan inverse of b upon a, and theta was always between pi and minus pi, including them both, and r was said to be the modulus of z, or the absolute value of z, which was written as root over of a square plus b square, right? These things we know. We also know that the complex numbers can be plotted on a plane which is called the Argand plane, which is similar to the usual R2 plane we have, where suppose this point is z, x plus I y. So specifically this is the coordinate xy. Okay, so this is specifically the coordinate xy. So if we consider this to be the x axis and this to be the y axis, so this is basically the point x, and or rather let me just consider the points a b. So this is a plus ib, so this is the point a and this is the point b. Okay, then this becomes the angle theta, and this distance becomes the angle, becomes the value r. So these things we know, but our main goal of this lecture is to bring out how this complex field C is constructed, to have a fair visualization of how things usually happen in C. Okay, this very construction also enables us to explore the topological properties of C very easily without having much problem in diving into it. Clear? Okay, so now the prerequisites I would say for this part of the lecture is having knowledge in field theory. We do not need much deep knowledge, just basic knowledge of field theory, it will do. Okay, so how do we do it basically? So we know that suppose K is a field, let's say, let K be a field, let K be a field, and let Px be an irreducible polynomial of degree greater than equal to 1 in K, and let alpha be a root of Px. Okay. Now since P is irreducible in K, so it is obvious that alpha being a root of Px, it is obviously not in K, right? Okay. Uh, so what we do is that we kind of extend K to a larger field, K being a subfield of that field, and this root is in that very field. Clear? So we take that field to be K alpha, which is isomorphically defined as Kx over the ideal generated by this irreducible polynomial. Now why is basically this a field? So see, K is a field, right? So Kx becomes a PID. Okay. So K is a field, which implies Kx, that is the polynomial ring of K. So this is a PID. So since P is irreducible, hence the ideal generated by P of x rather, is a prime ideal, and which implies it is a maximal ideal. It is a maximal ideal, and since this is a maximal ideal, so the quotient field constructed over a maximal ideal becomes a field. Okay. So sorry, I just told it to be a quotient field. So quotient ring constructed over a maximal ideal is a field, and since K alpha is the isomorphic copy of that very quotient field, so it is obviously a field again. So K alpha is basically termed as a simple extension of the field K. Clear? Okay. So so alpha is obviously in K alpha, and so K alpha basically completes the polynomial Px. This Px is said to be the minimal polynomial of alpha over K, as it is the irreducible polynomial of which alpha is a root and the polynomial is in K. Clear? Okay. For example, suppose we take this polynomial, say x square minus 2, which is in Qx. Okay. Then obviously x square minus 2 is irreducible in Q, right? Irreducible over Q, right? Because root 2 is a root of this polynomial, and root 2 is obviously not rational. So this field Q root 2, which is an isomorphic copy of Qx over the ideal generated by x square minus 2, is the required field, of which Q is obviously a subfield and contains the root of x square minus 2. Clear? Got it? Now in such a case, when such a case happens, that is in this case, this K alpha forms a vector space with respect to, I should say, with respect to K. Okay. And the dimension of the K vector space K alpha, which is also denoted as K alpha colon K. So this is basically the degree of the minimal polynomial of alpha over K. Clear? So if I extend this to this example, then the degree of this vector space Q root 2 over Q is basically 2, because the degree of x square minus 2 is 2, and it is the minimal polynomial of root 2 over cube. Clear? Okay. So we extend this very concept only because we have defined this for an arbitrary field, right? So we can obviously apply this to R. Clear? So what we do is that, so x square plus 1, which belongs to Rx, is irreducible, right? Is irreducible. So consider the quotient field. Consider the quotient field Rx over x square plus 1. Clear? Clear? Now obviously the root of this polynomial will be root over of minus 1, right? So this quotient field must be isomorphic to the simple extension of R with root over of minus 1. Clear? Now our claim is basically, or rather this is now very much clear to see, that this very field is our required complex field C, where we just denote this root over of minus 1 as the symbol iota or I. Clear? See, a few things are already clear. First of all, in this field, x square plus 1 has a root. Okay. The only polynomials which do not have a root in R are those whose roots are, whose roots are such that their squares are negative, right? Now, if the square root of minus 1 exists in some field, then all the other such elements whose squares are negative also exist, evidently, because see, consider the element C times root of negative 1, where C say belongs to R. Clear? So if you square this, what do you get? So C squared times minus 1, which is minus C squared, and since C is in R, so, or rather I can just say that C square is positive. So if C squared is positive, then this value is negative, so the square of this very element is negative. So we are done, right? So it was just enough to find a field, find an extension field of R such that the square root of negative 1 exists in that field, and that will do everything, right? Okay. Because see, if that happens, now this field obviously is a vector space over R. So if it is a vector space over R, then it is closed under the multiplication by elements of R, and if so, this happens, right? Well, that is all what we needed actually do, right? So we have actually constructed the algebraic completion of R. Now we are just left to just modify this very field R of root minus 1 to our known complex field C. Okay, that is the elements A plus IB form. That is all what we need. Okay, and once we have done so, the other properties will be pretty much just in your mind, right? Because you are already quite acquainted with studying the complex field, or the complex numbers rather. Now the after we introduce the term I, which is obviously the square root of minus 1, now we have named every number of the form A plus IB to be, or rather I should say, every number of this form Ci to be an imaginary number. And the only reason of that, because we have named those numbers whose squares are non-negative to be reals, so the numbers whose squares are negative to be imaginary. So that is basically a literal sense of naming the number. So there is nothing much to do there. Okay. So let's see. So what we do is basically okay. So what we do is, let's say, we define a, a quotient field homomorphism. We define a, a natural field homomorphism. Let's just a natural, because this term is pretty much there. A natural field homomorphism from Rx to Rx by x square plus 1, such that, so basically every polynomial px this just gets mapped to px plus x square plus 1, okay, via say the homomorphism phi. And this natural homomorphism exists in every abstract object, right? You have a natural homomorphism in groups, right? From an arbitrary group to its quotient group. You have it in rings, from an arbitrary ring to its quotient ring. And obviously then it also is there in a field, so it's from a field to its quotient field. An important property of a field homomorphism is that if it's not a zeromorphism, then it's obviously a monomorphism. Okay, we're not going to prove this, I'm just going to write it that if phi is a field homomorphism, then phi is either a zeromorphism in the sense that it just maps every element to 0. 0 is the additive identity, okay, or is a monomorphism. So monomorphism is basically a 1-1 homomorphism, okay. Now this is quite obvious from the definition of this natural field homomorphism that it is not a zeromorphism, right? So it will be a monomorphism. It is a 1-1 homomorphism. Clear? Okay. Okay. So what we have all have discussed here, just note it down once, that we have successfully constructed a relevant structure of an algebraic completion of R. We have showed that in that algebraic completion there exist numbers whose squares are negative. We have also essentially discovered the fact that that very algebraic completion is a field, which has come straight away from the fact that the quotient field we have constructed is with respect to a maximal ideal, right? Okay. So the only thing which we are left is just to construct the uh, the formation of the terms in a complex number, okay, the elements in a complex number, okay. So let us start with it, okay. Okay, so okay, let me use the, okay, 5 will do, okay. So the mapping is clear, right? Okay. Now let I be equal to x plus x square plus 1, which is nothing but the image of the polynomial x in Rx, clear, where x is in Rx, clear. Now notice what happens. See, what is I squared? So I squared is phi of x whole squared, and by the properties of homomorphism, so it is phi of x squared. Now we can write x squared as x squared plus 1 minus 1, again using the properties of homomorphism, so it is phi of x squared plus 1 minus phi of 1. Now what is phi of x squared plus 1? This is basically x squared plus 1 plus the ideal generated by x squared plus 1, which is essentially 0, right? So 0 minus phi of 1. Okay. Now since phi is a field homomorphism, it preserves 1. Okay. Since it preserves 1, we have this to be 1. So minus 1, right? Therefore I squared is minus 1. Now I should not say that it preserves 1 just because it is a field homomorphism. Rather it is a field isomorphism, you might say. Okay. Because it's 1-1, since it's or can we say it? Yeah, I think we can say it, because see, field is a 1 1, because it's a non-zero morphism, and for all elements px plus ideal generated by x square plus 1 in the quotient field, there is the polynomial px in Rx, right? Yeah, so it's a surjective. Yeah, it's a surjective map as well. Clear? So it preserves one. Clear? So thus we have essentially got hold of the symbol I whose square is minus 1. Is it clear? Okay. Now the rest of the things is pretty easy to notice. Why? See, we are pretty known to the fact that Rx is a Euclidean domain. Okay, it is an Euclidean domain. So what does that imply? So that implies there exists, or rather I should say, for all polynomials px in Rx, there exists a polynomial qx in Rx, and real numbers a and b in R, such that this px can be written as this qx times the polynomial x square plus 1 plus a plus bx. Okay, this is a simple extension of the Euclid's division algorithm to a polynomial field. Clear? Now, having done this, what will be the image of px in the quotient field? So this implies, so if you take phi of px, so this is equals to, so this becomes phi of qx times phi of x square plus 1 plus this is phi of a plus bx, right? So what is this basically? So phi of px is in the quotient field, right? So we do not manipulate this anymore. Now phi of x square plus 1 is 0, right? If you have an idea of what a quotient field is, then this is pretty much clear. Phi of x square plus 1 is 0, because this is of the form x square plus 1 plus the ideal generated by x square plus 1. So this is basically 0. Okay. So this whole term becomes 0. So this is, we are left with just phi of a plus bx, and this is nothing but a plus b of phi of x, because a and b are basically scalars here, nothing else. Clear? And what is phi of x? So phi of x we are taken to be I, so this is a plus bi. Clear? And phi of px is nothing but the field Ri, is in the field Ri. We are just using the notation I now, because we already know what I is. Clear? So that means every element in Ri has the form a plus bi, and that is all what we actually needed to do. So we have essentially constructed the elements in Ri, and this field Ri is what we term as our complex field. So this Ri field is what our complex field C is. Okay, so C is basically this Ri. Clear? Okay. So having done this, so having essentially constructing this very field, now our goal is to understand how this field actually works, and how we already had this field before, but we haven't had just didn't notice this field as a as having an individual existence. Okay. So first of all, notice this, that what is the degree of the vector space C over R? So it is basically the degree of the vector space Ri over R which should be the degree of the minimal polynomial of I over R, which is basically the degree of x square plus 1, right, which is 2. Okay, so obviously the dimension of this of the vector space CR, the dimension of the vector space CR is nothing but 2. Okay, moreover, we have noticed that every element in C has the form A plus IB. So that implies this set 1I forms a basis over the vector space CR. Clear? Clear? Okay. Okay. So, okay. Now how does this definition of the basis helps us? Okay. Or first I should have asked the question that why is this field C unique? And by the term unique, I mean it is unique up to isomorphism. Now this is pretty clear from the fact that C, since is an algebraic completion of R based on the polynomial x square plus 1, so it is basically the splitting field of the polynomial x square plus 1 over R. Okay, C is the splitting field of x square plus 1, which belongs to Rx, and splitting fields of a certain polynomial over a field K are unique up to isomorphism. Clear? Got it? So C is indeed unique. Okay. Now we want to discuss the properties of the elements in C. Notice this, that let A plus IB be equals to C plus ID. We know that this equals if and only if A equals to C and B equals to D, and we have done this in our junior classes, right? We have just stated this. Now why does this happen? This simply happens because 1 and I, this set forms a basis, right? So it is a linearly independent set. Since it is a linearly independent set, and from this we have that A minus C plus I times B minus D, this is equals to 0. With being a linearly independent set, so A minus C and B minus D must be equal to 0. So A must be equal to C and B must be equal to D, and the converse holds trivially, right? Clear? Got it? So having done this, we can say that the 0 element in C will be obviously when A and B both are 0, right? Furthermore, notice that C is a field with respect to operations which have been dragged down from the field R only. Okay, so C has the operations of algebraic addition and algebraic multiplication of R itself, nothing else. We have just eventually seen that when we have constructed C, right? So what I mean to say is that A plus IB plus C plus ID is nothing but the addition of the reals, which is A plus C plus I times B plus D. Moreover, the multiplication is a bit different, but it happens eventually by usual multiplication in R. How does this happen? Let's see. So A plus IB times C plus ID, we move forward using the usual distribution of multiplication we have. So we have A times C plus we have I times B, I times D, plus we have I times B times C, plus I times D times A, or rather I should obey the original order. So it is A times C plus A times ID plus IB times C plus IB times ID. Now obviously these are in reals, right? Each element A, B, C, D are in reals. So the multiplication is obviously commutative and the addition is commutative as well. So we can write it as AC plus I squared times BD, and from here we can take I common outside. So this is AD plus BC, right? Now I squared is negative 1. So this is AC minus BD plus I times AD plus BC. Is this clear, right? So this is the definition of multiplication we have in complex field. So if I write this as a, one second, so if I write this as a dot, so C plus dot as defined above, is a field. Clear? Furthermore, notice that suppose say we have this number A plus I0. So this is obviously in C, right? Okay, but this is eventually A. Clear? So this is obvious from the fact that R is in, I mean this is this obviously tells that R is in C. Clear? Now our goal is to identify C as an isomorphic copy of R2. Now how do we do that? So what we actually do is that we have a mapping from C to R2, let's say by alpha, such that every element of the form x plus iy is mapped through alpha to the coordinate xy, and we are done. This is just it. Clear? Everything can be proved from here that it is an isomorphism. Okay, a field isomorphism. Now having done this, notice that we can kind of imagine the real numbers as the coordinate of the form A0. Okay, and we identify I to be the coordinate 0, 1. Notice that then every complex number can be identified as, so a real number A0 plus iota, which is the coordinate 0, 1, times a real number B0, and if you apply the usual addition and multiplication, this will surely be of the form A comma B, and this can be plotted in R2 by plotting A along the x-axis and plotting B along the y-axis. Clear? So this basically means that the geometrical visualization of a complex number is nothing but the coordinate in the real plane having both the components of the complex number as the components of the coordinate, right? We name the plane of the complex, though it is same as the real plane, but we name it a bit differently just to ensure the differences of them in terms of their construction or in terms of their importance, I might say. Okay, so we name the complex plane as the argand plane. Okay, so the argand plane, so the argand plane is basically the R2 plane itself, where we name the x axis to be the real axis and the y axis to be the imaginary axis. Why is it so? Because in the real axis we plot the real numbers simply, right? Nothing else. And in the imaginary axis we plot those terms which are there along with the I, right? You can easily notice this from here. So if I have this number, sorry, have this complex number z equals to a plus ib, so it is nothing but the coordinate in the R2 plane. So if this is the R2 plane, it is the coordinate xy. sorry, it is the coordinate AB, right? Clear? This also ensures one more thing, that the topological properties of C are equivalent to the topological properties of R2. And since we are currently talking about complex analysis, so I'll obviously assume that you people are pretty much acquainted with real analysis, basic real analysis, and basic analysis of the R2 plane as well. So there is nothing much to talk about the complex the topological properties of a complex field, because it is exactly same as that in R2 we have. Everything happens similarly. Clear? So the topological properties of C are equivalent to those of R2 as well. Clear? Moreover, if we want to construct this field C from, or rather if we want to explore this field C in terms of coordinates in an R2 plane, then it is also pretty much easy, just by defining addition as the simple addition of coordinates, where we have say xy plus x dash y dash as x plus x dash, y plus y dash, and the multiplication is defined as the x dash minus y dash, xy dash plus x dash y, and this definition of multiplication is basically a conclusion from the multiplication we had in terms of complex numbers a plus ib, which we had done here, right? Yeah, this one, nothing else. Clear? Got it? Okay. So one more topic which we will discuss now, and we will end this lecture. It is basically discovering the polar form and the Euler form of a complex number, and then we will end this lecture. Okay. So before moving on to the polar form, let me just introduce the de Moivre's theorem. The de Moivre's theorem. So what is the de Moivre's theorem? So it says that cos theta plus I sin theta to the power n is nothing but cos n theta plus I sin n theta, and this happens for all n in integers. Okay. So how do we prove this? So we prove this using induction first, by just restricting n to the naturals. Okay. So let n be in n, we induct on n. So how do we do this? See, if n equals to 1, the statement is trivial, right? If n equals to 1, it's trivial. So the base case is basically trivial. So let the statement be true for some n equals to k, and we prove it for n equals to k plus 1. So what happens? Let's see. So cos theta plus I sin theta to the power k plus 1 is basically cos theta plus I sin theta to the power k times cos theta plus I sin theta. So this is basically now from the induction hypothesis that it is true for some n equals to k, so this is basically cos k theta plus I sin k theta times cos theta plus I sin theta. Now just having the usual multiplication, we have this to be cos k theta cos theta minus sin k theta sin theta plus I times say sin k theta cos theta plus cos k theta sin theta, and this is nothing but cos of k theta plus theta, which is k plus 1 theta, plus I times sin k theta plus theta, which is sin k plus 1 theta. and hence we have proved using mathematical induction for all natural numbers. Got it? Now what do we do? Now see, for n equals to 0, it's again trivial, right? So it's 1 and cos 0 is 1, right? So for n equals to 0, cos theta plus I sin theta to the power 0, which is equals to 1, which can also be written as cos 0 plus I sin 0, because sin 0 is 0 and cos 0 is 1. So it's again trivial for n equals to 0. So we need to prove it for the negative natural numbers, and that is pretty obvious if we have just proved that this happens for negative 1, because every other negative natural number is just a natural number times minus 1, right? So cos theta plus I sin theta to the power minus 1. So this is 1 upon cos theta plus I sin theta. So we just rationalize it. So it is cos theta minus I sin theta, and below you will have cos squared theta plus sin squared theta. So this is basically, now see, so denominator is 1, the numerator can be written as cos of minus theta plus I sin of minus theta, just because cos theta is an even function, right, and sin theta is an odd function. Clear? So sin of minus theta will be minus sin theta, and cos of minus theta is simply cos theta. So therefore statement holds for n equal to minus 1, which implies holds for all negative natural numbers. And since we have already proved it for the natural numbers and 0, so this implies that this holds for all n in Z. Clear? But our question is that, is de Moivre theorem true for all rational powers as well, or for irrational powers as well, or for real powers as well as or for complex powers as well? And that is basically true by the extension of the de Moivre theorem by Euler using the Euler formula. So what has Euler done basically? This is also pretty easy. So let me just change the color. So notice that, from the Taylor series expansion we have the following series, right? So we have e to the power x to be 1 plus x square upon 2 factorial plus x cube upon 3 factorial. Sorry, I missed the x part, right? So this is 1 plus x plus this plus x to the power 4 upon 4 factorial plus x to the power 5 upon 5 factorial, and so on, right? Now if I replace x with I theta, what happens? So we have 1 plus I theta plus, so I squared is negative 1, right? So this is minus I theta square, sorry, minus theta square upon 2 factorial. Now here what happens? So I square is minus 1, that means I cube is minus I, right? So this is minus I theta cube upon 3 factorial. Then I to the power I square is minus 1, so I to the power 4 is plus 1, right? So this is plus theta to the power 4 upon 4 factorial plus, again since I to the power 4 is 1, so I to the power 5 is I to the power 4 times I, so it is I. So this is I theta to the power 5 upon 5 factorial, and so on, right? Now remember that what should be the expansion of cos theta? So this is basically 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial, and so on, right? Alternate plus and minuses. And then we have the sine theta, it comes out as theta minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial minus, and so on. So if I multiply just I with this, so this becomes I, here is an I, here is an I, and so on. Now notice that e to the power I theta, see you have cos theta terms here, right? See 1, 2, 3 and so on, and you have sin theta terms here, right? So 1, 2, 3 and so on. So e to the power I theta is nothing but cos theta minus I sin theta, sorry, plus I sine theta. Right? Now, what is the use of this? So now if you take any power, irrespective of what it is, whether it's rational, irrational, or anything, so e to the power I theta times any power n. So this is basically e to the power I n theta, and which should be nothing but cos n theta plus I sine n theta, and e to the power I n theta, I theta to the power n was nothing but cos theta plus I sine theta to the power n. Right? So that means the de Moivre's theorem holds for all n's. Clear? Okay. So this lecture is already pretty long, so we end this lecture right here. In the next lecture, we will be studying about the conjugation of complexes, the absolute value, defining a metric on a complex field, how a metric is defined on it, and that will also be equivalent to the metric, the Euclidean metric defined on R2, and the other topological properties in brief. Okay, so meet you guys in the next lecture.